Okay, so now that we've gotten our measurements out of the way with our demonstration lab assistant, then we're going to move on to talk about some of the calculations and the overall flow of the lab. Okay, so one thing that I want to stress in all seriousness is I'd highly recommend reading the introduction. I think I wrote it fairly clearly, and there's there's a lot of steps to understand, and you'll get a lot more out of the lab if you just read through the introduction, so you have that. So please don't skip it. It will serve you well. Okay, the procedure as well, right? So obviously the video is going to supplement that procedure, but the thing is that you have the this as a reference. Okay, so the procedure I would say is a key reference. If you want to refer back to something that you didn't quite understand, maybe seeing it in writing will make more sense. Okay, so now let's actually move on to answering the questions that really kind of walk us through the whole lab and are really directly referred to in the procedure. Okay, so one of the things that we did right away in the first part of this video is we measured the distance to the anglometer, which is that piece of cardboard, right, which you can see here, right, the unmarked cardboard, which I have since marked up, by the way. You'll see that in a minute. And so we measured that distance from the cardboard at arm's length to my daughter's eyes, okay? And we got a value of approximately 18.5 centimeters. Now, you wouldn't want to make multiple measurements. You're not going to have to be holding a camera at the same time, so I would expect you to make measurements more carefully than I did. For example, you can see here that the ruler or the measuring stick is not in a direct line with the eyes, right? It's kind of coming out towards the camera. That's going to affect the measurement, so essentially you're only getting a component of it. A component of that angle that you actually want to measure, it's parallax itself, right, at play. So have it touch the eye as directly as possible. But when we take this rough measurement and we convert it over to centimeters and a single measurement, where of course you're going to be making 3 repeated measurements, we get 47 centimeters, and that's the number that I'm going to go ahead and use. Okay. So I do want you to discuss, the process that you did to make your measurement as carefully as possible. Okay, so now let's talk a bit about the calculation, because one of the first things you do, and one of the first key calculations, which can be a sticking point in this lab, is you want to calculate a distance. The distance you want to calculate is this distance right here, all right? So you want to find out how long this distance is going to be in centimeters. You haven't marked the cardboard yet. For example, when I calculated this distance, the cardboard was still blank. You're calculating that distance so that you can mark the cardboard. It allows you to calibrate the anglometer, okay? Because you want each of these red large tick marks, all right, to correspond to 1 degree. You want them to correspond to an angular measurement of 1 degree, okay? That's the angular size. That's dependent on whoever's arm is holding it and the length of that arm. All right, so in the case of my daughter, let's see what happened. All right, so the formula we're going to use is the small angle approximation converted over to degrees, so specifically this side of it, all right, which you can see I reproduced over here. All right, now remember, this is all described in the introduction, that big D is the diameter. All right, this would be like the diameter of the moon, for example, and it's also going to be the diameter of the tick marks. So it's the distance between 2 of those red tick marks. All right, so D would be this distance right here. On the other hand, little d is the distance. Little d is the distance from the eyes to the cardboard, to the anglometer. All right, so that distance right there, that's little d, lowercase d. Okay? So yes, little d is larger in magnitude than big D, but it makes sense for big D being diameter and then little d being distance. Okay? So what we want to do is we want to make sure that we have one unknown value here. And in this case, that single unknown value is going to be the distance between the red tick marks, because remember, that's the whole point, so we can put them on the cardboard. So we're going to leave D as our variable. We want that D to correspond to 1 degree, as described in the procedure, all right? And we want it to match up with my daughter's arm length of 47 centimeters. And remember, this 57.3 is just there to convert from the way the formula is basically derived, the basic formula, over to degrees, right? So this is the conversion from radians to degrees, all right? So that's discussed in the introduction, and for your purpose, it's just part of the formula, okay? So we're going to rearrange this formula, which is going to involve multiplying both sides by 47, so that it cancels out over there on the right, and we end up with 47 on the same side with the 1 degree. And then we're going to additionally divide both sides by 57.3 degrees. So divide both sides by 57.3, cancels them out on the right, and that will leave us a 57.3 over there on the left. Now, since the thing we're solving for is D, it's going to make sense then to switch everything over. So then we're just going to rewrite it, the mirror image of that equation after rearranging, right, and doing the math I just described. So we get d by itself shown over on the left, since we read from left to right, right? And here we have the ratio of those degrees, okay, so that it's going to, the measurement you get is not going to be in degrees because the degrees effectively cancel out. So you just have 1 over 57.3 and then multiplied by 47 centimeters, okay? So that's going to give you the distance between the tick marks in centimeters. Remember, it's not giving it to you in inches, right? If you left this in inches, which I don't want you to, right? I want you to be using the metric system, then you would be getting a distance on the cardboard also in centimeters, okay? But go ahead and convert everything over to centimeters. So that's telling me that I better mark, marks along the cardboard that are exactly 0.82 centimeters or as close as possible apart. Now, this is actually a pretty small distance, and that's because my daughter's arm, being an 8-year-old, is pretty short. So likely you're going to have a larger distance because the bigger the arm length, the bigger the value of d, all right? Because remember, you've rearranged and d is over here. So the larger value of d, the larger value of big D, the diameter, the distance between the tick marks, okay? So keep that in mind. You should get a bigger number than this, right? And it was a little difficult to actually, get those tick marks, to be 0.8 centimeters apart, right? I did my best job here, right? So these are all approximately 0.8 centimeters apart, all right? And they're really clustered together. Again, a limitation of having a child with a relatively short arm, be the person holding the anglometer, and that anglometer being specifically calibrated to that person, right? Because if I wanted to make an anglometer for myself, I would have to calibrate it to my arm length. Okay, and then as described in the introduction, there needs to be divisions within each of those 1 degree measurements, because this is a physical distance of 0.8 centimeters, but it corresponds to an angular measurement of 1 degree, right? So it says anything that fills this size when you're holding up an anglometer at arm's length and partially blocking something, and you look at the size of that thing, well, that object then has an angular size that you can just read off of the scale here, right? So if some object like a tree or something, right? Over here, the trunk of a tree, right, went from one edge all the way to the edge of the 5th tick mark. That means that it'd be 5 degrees in angular size. Okay, it wouldn't have a size of this many centimeters, 4 centimeters, right? Because that doesn't make sense, right? It's all about the angular size, how much of your field of vision that object fills up, which of course what you'll be doing when you look at the angular size of the moon. But as I was saying, then you're putting smaller tick marks in between. You put 3 in between so that there's 4 divisions. That means that this smaller distance here is 1/4 of a degree. Okay, since it's one quarter of a full degree angular distance. Okay, so there we go. We have our calibrated anglometer. Here I zoomed in and showed the actual measurement and how I was able to space out those marks. Here is something like the picture that you would include of your anglometer. You can see how they're all clustered together, not filling up much space. Although I never expected to fill up the whole cardboard, right? But I would have centered it more if I had been thinking more about how close they were to be to get how close they were going to be together. But it doesn't matter. It's still a completely functional anglometer as long as my daughter uses it. Okay, so there we go. Right, there's the whole process of calibrating your anglometer. Now, going on to the next part of the lab, which is using a different approach, but all the same math. So instead of having a measured distance, we're now going to have a as in little d, we're going to have a measured big D, right? We're going to have a known distance between 2 points, and then we're going to see the angular effect. Okay, and so I mentioned this in the first part of the video. It was the second measurement we made that preceded my daughter holding up the pencil and then closing one eye at a time, so that she could see how the pencil shifted and blocked different objects, and then get an idea of what was the distance between in that case used to calculate the distance between her eyes and her hand holding the pencil. So a way to actually calculate the length of your arm, okay? Because that's how astronomers use parallax to calculate the distance to relatively nearby stars, seeing their shift over a calendar year, relative to more distant stars, because the astronomical equivalent of closing one eye at a time and seeing that shift back and forth of the pencil is the Earth going from one far end of the orbit to the other far end of the orbit on the other side of the sun, right, looking out towards distant space, which is 6 months of time, right? But over that distance, which is about 300 million kilometers, that's what's called the baseline. That's the difference between the two observation points. So in this case, and that's a known distance, right? We know that distance from a number of other techniques astronomers do. They can even bounce lasers off of nearby objects like Venus, and then basically get really direct measurements of the size of Earth's orbit. Okay, as well as just confirming that it matches our understandings of basic, orbital physics. Okay. But here we just took a direct measurement. We didn't have to bounce any lasers or consider orbital physics. We just measured the distance between our 2 points, which were the 2 eyes of my daughter. Okay, and we look here, and we're going to say that corresponds to 7 centimeters, I think. For again, take a rough measurement. You obviously will be able to make your measurement better. I certainly hope. All right, so we'll say 7 centimeters is approximately our value. I'm just reading that off of here. All right, so approximately 7 centimeters. Okay, and you'd want an average. Then we're going to report the angular separation between two distant objects. Okay, so we're going to use the angulometer calibrated to her arm length, but we're going to sort of naively ignore the fact that we already know her arm length and just confirm that we can calculate it. All right, so we're going to so as we discussed in the video, the first part of the video, she was holding up that pencil and kind of doing it by just holding up the pencil. But at some point, you're going to want to, or pen or whatever, you want to hold up the pin and the angulometer together, right? So you can see that angular shift and move the angulometer to actually see exactly how much is changing. And what I'm referring to is basically this idea here. You want to know the angular distance between these 2 points. All right, so here, let's get color that's going to show up well, right? Because you're holding this right, the pin, right, going back and forth between, just two distant objects. And in this case, the distant objects are just large, single color squares, right? But there could be trees or mountains or anything, right? Anything in the distance, houses or whatever, right? And so then you're going to measure, having your angulometer right down here, right underneath, right? So it's just sort of not blocking your view, but is visible within that same view, right? You're going to have your tick marks, right? Spaced, 1 degree apart with the smaller ones in between. And that's going to be how you're going to know exactly what is the angular shift. So in this case, in my rough sketch, this might be, say, about 4 degrees, right? Between the 2 points. All right. So that's what you're going to report for number 6. So we could say, we have something, again, this is just a guesstimate value here of about 4 degrees. We would have used the angulometer, okay? Then you're going to use your calculation, or it says here, to show your calculation for the distance from your eyes to your hand used to hold the pen, okay? Like question 3, you'll be rearranging question 2 to find this value of distance. Okay, so what's going on there? Well, that's just solving for big D. Now remember, the formula told us that theta, measured in degrees, was equal to diameter, all right, which are the marks on the the angulometer, right? Well, yes, they were the marks on the angulometer in the first part when we used it. Although here, what is D, right? Well, I can tell you up here, it's what's called the baseline, that term I used, which is kind of a jargon term for this idea of parallax. And again, for astronomy, the baseline is those 2 points half a year apart in Earth's orbit. But here, our big D is going to be that 7 centimeters. Okay. All right. And then that means what we're trying to solve for is little d, which is going to be the distance to the angulometer, to the thing that we were looking at, that we were observing shift back and forth. So the pin was playing the role of a relatively nearby star, just a few light years, or 10, 20 light years away, right? So which is a nearby star in our neighborhood, relative to much distant stars, which would be thousands of light years away, which don't show any noticeable parallax. Okay, and then we have our 57.3 degrees, right? So, and we're going to solve for little d, which is going to involve rearranging. I showed you one example of rearranging, so I'll leave this one up to you. But then you would just solve for d, okay? And that d is going to be the length of your arm. Length of arm. All right. And yes, you already know it, but you're just going to confirm that it works, right? You're going to confirm the approach here. And remember, this angle is the one you directly measured by noticing the shift of the pin, like I was talking about when I flipped back to the procedure. So in our case, maybe this is about 4 degrees. Okay. All right. So then how does this calculated value of distance, d, right, length of your arm, compare to the value directly measured in question 1, right? So like, how does, whatever we got for d from this calculation here, from the one from 7, all right, how does that compare to the D that we directly measured as, was it 47 centimeters? Yeah, 47 centimeters, okay? So you could say that this is the measured, and then this is the calculated. C for calculated, M for measured, all right? And you'd have both those values, because in 7 you would have calculated the calculated version of distance. Put that subscript there again. And so then you're going to do what's called a percent difference formula, and that's just going to involve, right, having the measured minus the calculated divided by the average of the two. So specifically, what that would look like in this case, right? So we'd have, and it's the absolute value because you don't want a negative here. So you'd have dm, right? That would be the 47 in our case, minus the calculated, whatever you get from number 7 above, and then divided by the average of the two, which would just be taking, when you take the average of two numbers, you just sum them and divide by 2. All right, and then you multiply that by 100 to turn it into a percentage, and that is your value, the percent difference between the two. You want that percent difference to ideally be as small as possible, because that would confirm that you were making careful measurements, which is great, because then when you go on to actually measure the moon, you hopefully have this whole process down, you kind of understand it, and then you are capable of making careful measurements. And if not, maybe you got to make a new anglometer. Okay. All right, so this part of the procedure is where we're going to actually go ahead and measure the distance to the moon. So let's see. So in the first part, considering these differences, which are listed above, right? Why would astronomical parallax, as described above, not work for measuring the diameter of the moon? Okay. So right. So this is all follow up for part 2. Excuse me. All right. This is an open question. How do you think astronomers were first able to estimate the diameter of the moon? Right. So this is all this is some speculation. You can look in on astronomy resources. You can kind of just think about the idea here. But what I'm clearly hinting at here between questions 9 and 10 is that this method, the method described in part 2, is great for measuring the distance to stars, right? Using this idea of the baseline, right? The 2 points in Earth's orbit, but is totally useless for measuring the distance to the moon, because the moon doesn't have a baseline, or the Earth doesn't have a baseline relative to the moon, right? So how could you actually measure the distance to the moon, right? There's a number of different ways. I think that at least I can think of at least 2, that I think you could describe well. So that's the idea, all right? Of your answers, and this is just your as clear as possible answer the questions 9 and 10. I'll be looking at your thought process and your clear argument, as well as your understanding of astronomy. So now on to measuring the distance to the moon. Okay, so now for part 3, right, which is really kind of the culmination of this whole process, we're going to use our anglometer, our calibrated anglometer, to measure the angular size of the moon. Right, so that's the beginning. Right. So, we're going to get that anglometer out. We're going to hold it up on a night where the moon is in any phase that isn't new or crescent. So a quarter moon, a gibbous moon, or a full moon will all work fine for getting a measurement. Obviously, when you measure across the moon in a phase that isn't precisely a full moon, so imagine, we have some phase of the moon which is maybe nearly full, right? So let's draw a circle, and then we'll cut a little bit of it off, right, to kind of signify that we've, the moon is not quite full, right? So maybe the moon looks up something like this. Well, when you measure that distance, that's going to represent the angular size of the diameter of the moon. You obviously don't want to measure it this way, because you would be underestimating it. So you want to find a point that is straight across, all right? So this would be your angular size for the diameter of the moon, okay? You're going to do this multiple times by holding the anglometer up to partially cover the moon, right? Your calibrated anglometer, and get that angular size. So what you're going to report for 11 is an angular size, okay, in degrees, all right? Then you're told the actual angular size just below, right? You're told that it is 0.5 degrees, at least accurate to a tenth of a degree. So how close was your value in degrees? Does it seem acceptably close? If not, what do you think went wrong, right? So this is a key point where if you're not close, something did go wrong, because there's no reason that you wouldn't be, within, maybe 0.6 or 0.4, but certainly in that range. If you're getting something like 2 degrees, either your anglometer is miscalibrated, or you're not holding it at the same distance, right? Maybe you're not holding your arm the same, or you're doing something wrong in terms of holding it up, relative to the moon. Okay. But then, assuming that everything went well there and you're able to check out that you had a good measurement, we're going to proceed with the last of the calculations, which is actually using that angular size measurement for the diameter of the moon to calculate the distance to the moon in kilometers. Okay, so all right, so we got an acceptably close value, right? So we're going to go ahead and proceed. Okay, and it says to make this calculation, all right, we're going to consider that the diameter d of the moon is known. All right, so there's other ways besides measuring the distance to the moon that have been used since ancient times, as mentioned in the previous question, that the diameter has been known. Okay, so the diameter of the moon we assume is a absolutely an independently measurable quantity. Okay, and we know that it is 3,476 kilometers. All right, so big M for moon, and 3,476 kilometers. Now that's the distance. That's a unit we're going to keep using. Just like in parts 1 and 2, we were using centimeters. Here we're going to stick with kilometers. All right. So now we're going to go ahead and let's see. So we're going to show your calculation using equation 2 rearranged, and then as I say, your answer should be in units of kilometers. Okay. Yeah, so, oh yeah, and this is where calculating D. Let's see, so this is going to be, the same approach of rearranging and solving for D. So remember, I've little d, right, to be clear. I did show you that example of solving for big D, and then I said that, I will leave the algebra up to you to solve for little d. Same thing here, but that is what you're going to want to do in this part. You're going to solve for little d. So as a reminder, the formula is theta equals the actual diameter of the moon, which is a known quantity. You'll plug that in, all right? And then you have your calculated value. This is what you're going to be solving for, little d. And then you have the conversion over 2 degrees, right? And then over here, you also, for theta, this is what you just measured in question 12, right? So, and this should be something around, right, half a degree. Okay, measured directly with the angulometer. All right, and then solve for little d. And then besides showing the calculation, you're going to show the value, right? So you actually have d as some number with kilometers clearly reported in this question, right? In the area provided. Then you're going to compare your measured value to the actual accepted value. And this could be, with modern techniques, this value here could be used by, as I said before, bouncing a laser beam off of the moon and measuring the travel time of that laser beam, which is a really accurate way of measuring distances, all right? Up to, a few million kilometers, right? Where it's realistic that you can, detect that light coming back, the reflected light coming back from the moon. All right, the moon is quite reflective too. Okay, so then you're going to do a percent error here. So instead of a percent difference, this is a percent error, because instead of comparing between two measurements, you're comparing between a measurement and an accepted value, right? A value that is, like published and accepted. Okay, so the formula is similar to the one we saw before, but it's slightly different. So it's a percent error formula rather than the percent difference. It is, again, the absolute value up top, so you don't have a negative, but it would be the measured value, so little m for measured, right, because that's what we found up above. So that same subscript, little m, big M for moon, by the way, and then minus d, and then I'll put the big M here for the accepted, all right? And then the key thing to remember about the percent error formula is that, the denominator is different. Instead of an average, it's always the accepted, because you're asking yourself, how close did you get to the accepted? And so the accepted is none other than this value right here, right? So then we're just going to put that down in the denominator, multiply by 100 to turn it from a proportion to a percent, and that's what you're going to report, okay? Show your calculation and your answer and the area underneath 14, right? Then you're going to, ask yourself, how did things go? What was the overall results? And that wraps things up, okay? So I hope this gives you a good direction on how to do the lab, how to do the calculations, and the point of it all. And thank you so much for watching this instructional video. Bye for now.